Being at CppCon has been amazing because you can directly speak with the experts. I've had conversations with Bjorn Strusepp, with Sean Parent, and they're all very friendly and accessible and willing to give their opinions or advice on C++.
Well, thank you for coming to my talk. It's leveraging a functional approach for more testable and maintainable ROS2 code. So before I get started, I just want to get the lay of the land and my audience. How many of you here are roboticists? Cool. How many of you use ROS2? All right, a bit less than that. How about other sources of middleware? No one else? OK, so this talk is catered towards people who use ROS2, but I think the topics and the approach that I talk about in this talk will be applicable to other sources, like other middleware-based code. So with that, let's get started. So this is what I'm going to cover in today's talk. I'm going to go over what we do at Picnic and how that motivated this talk. I'm going to talk about what is ROS2 and show some code that can be considered the typical ROS2 approach, as well as testing that code. Then I'm going to introduce functional programming principles, and we'll refactor that conventional code using those principles. And finally, we'll go over what the main takeaways are. So, introduction. About me, my name is Bilal Gill, as I'm sure you guys know. I'm a robotics engineer on the services team at Picnic Robotics. I've been there for about a year and change now, and in that time, I've worked with different clients. I've contributed to a number of projects, ranging from remotely operated underwater vehicles to agricultural robots. Before that, I worked at General Dynamics Electric Boat and MIT Lincoln Laboratory. And I like to think of myself as someone who's been interested in robotics since high school, right? So this is something I find really cool, and I think it's an honor for me to be up here. So in my free time, I'm more of a hobbyist roboticist when I'm not being a professional roboticist at work. So about Picnic Robotics. We are considered the unstructured robotics company. Unstructured is basically when the robot is required to perform tasks and do things in an environment that's not predetermined or predefined in any way. As a counterpoint, sorting objects can be considered a structured robotics problem. It's very constrained for the most part. Picnic Robotics is we're the main maintainers of MoveIt. And MoveIt is an open source robotics manipulation platform for developing robotic arm applications. But not only that, Picnic Robotics is developing MoveIt Studio, which is a software development kit and developer tool that leverages MoveIt to make it easier to create robotic arm applications. But last but not least, we also provide consulting services. So if you guys need consulting services, you should come to us. But we also perform feasibility studies and develop robotic software. So with that, why use ROS? Or Robot Operating System. It's the de facto middleware of choice in both academia and industry across robotics. And it's sort of a misnomer. It's not actually an operating system. It's a set of software libraries and tools. According to the ROS 2022 metrics report, more than 740 companies use ROS, so it's not an insignificant number by any means. And the report was published by Open Robotics, who are the current maintainers of ROS. So with that, using ROS allows Picnic to leverage open source software to quickly develop code for our clients and for internal use also. A bit more information, there are over 2,000 ROS packages available for use, and they vary from state estimation to motion planning to inverse kinematics and more. And like I mentioned before, Picnic maintains one of the most popular open source packages, MoveIt. So given that, why am I up here giving this talk, right? So engineers at Picnic experiment with different ways to architect code that use ROS2. And we want to create code that is easy to understand, test, maintain, and extend. When we work on a services project, we follow best practices, but we have the freedom and leeway to experiment with new ways to architect our code. At the end of a services project, our code is handed over to the client. So how can the client expect proper operation of the software once they start developing on top of it, right? We got to write a lot of tests and a lot of documentation because, if they want to come back to us for help, that's going to cost them money. But the thing is, though, we don't want tests that are flaky. If any of you, for those who don't know, flaky tests are tests that return both passes and failures despite no changes to the code or test itself. So it's sort of like a Schrodinger situation. You don't know what you're going to get until you get it, right? So ROS2 documentation encourages an object-oriented paradigm that can lead to trouble writing code that achieves the goal. And in the conventional code example, you'll see exactly how. And this is sort of like the goal of this talk, and what I want you guys to take away from it is that adopting functional programming techniques into our code, both for product and services, has made it easier to test, maintain, and extend that code. So I'll talk a bit about what ROS2 is. So like I mentioned before, it's a set of software libraries and tools. But ROS2 also has a middleware layer that allows for message passing between different processes. So in a robot, there are multiple parts that need to communicate, like sensors and planners, and this helps facilitate that, right? In the ROS2 systems are made up of nodes that can publish data to topics, they can subscribe to topics, they can act as service servers, they can act as service clients, so they can do a bunch of things that are really helpful. They provide configurable parameters which can be adjusted at runtime, which is really nice. And using ROS2, we can also log telemetry data that is useful for introspection if things go wrong out on production, right? So over here, I have an example of a ROS2 system, and there's 2 nodes in the system, as you can tell. Node 1 acts as a service client and sends requests to Node 2. And Node 2 acts as a service server, receives the request from Node 1, and sends back responses. Node 2 also uses parameters at runtime to change its behavior. So hopefully you get a better idea of like the ROS ecosystem with nodes. Thing is, we want each node to be responsible for only a single thing, right? For either controlling motors or publishing sensor data, things like that. And the publishing and subscribing of data and service requests is done via the ROS2 API. The straight lines you can see connecting the nodes, you can imagine them as the middleware, which carry the request from one node to another. So now I'm going to talk about this example that I'm going to carry out throughout the rest of this talk. So imagine this problem, right? We have a robot that wants to navigate from its current location to some goal. The robot needs to know where all the obstacles are located in its environment. So we have this something called the occupancy map. It's a data structure used to represent the environment around a robot in terms of how occupied the cells in the map are. So in other words, an occupancy map contains confidence in how likely each cell is to be occupied. But for the purposes of this talk, we're only interested in cells that are completely occupied or completely free. So, just for the purposes of this presentation. We're going to make a simplifying assumption here, that the robot knows its location in the occupancy map at all times. If we didn't make the assumption, we're going to have to perform localization and state estimation. So let's keep that problem to like actual robots and not our little toy example. So our solution for this problem is that we're going to have the robot send a request to a ROS2 service that generates a path from the robot's current location and goal location, given some occupancy map. So now I'm going to go over what the ROS2 conventional approach is. So here's some code I've written, and this sort of encompasses the ROS2 conventional approach. If you've worked with ROS2 before, this is something you've probably seen. You've seen something very similar to this before, if not having written like something exactly like this, right? So the paths generator class will be used to generate the path for our robot. And like I said, this code was written using example code available from the ROS2 documentation. And I'm sure you guys can tell, but this implementation follows like an object-oriented approach. So I'm going to go through the code and just note things of interest, right? So we know that path generator inherits from RCL CPP node, making it inextricably linked to the ROS2 API. Because of the way that ROS2 is architected, we now depend on the runtime environment to test this class. We have the setMap service and generate path service that I've outlined, and those are callback functions that run when requests are sent via the ROS2 middleware. Those functions call the set cost map and generate global path functions, which are private functions that contain the actual business logic. And just to give more context on why everything is private here, right, is I'm the author, and I don't really intend these functions to be called directly, only through the middleware. That's why it's natural to make everything private. And this is sort of the code that you see in like the ROS2 ecosystem if you search ROS2 code online. So let's take a closer look at the path generator constructor. So robot size is a parameter that is required to construct the collision checker object in our path generator. It's common in ROS to fetch parameters in the constructor of the node, right? But this leads to a pattern of dynamically allocating the object because it can't be initialized in the initializer list of the class. Another option is to not have collision checker be a unique pointer, but instead be a normal object inside of the path generator class. Thus, when a collision checker is created, it's a partially initialized object. To actually initialize the object, we'd have to have some sort of initialize method, which collision checker uses, and that's where we'd pass the robot size parameter. The thing with partially initialized objects are that if we try to use the object before it's been initialized, it can lead to bugs. It's pretty hard to reason about because if you're not sure you have to initialize this object, it's something you're gonna have to dig deep into, right? And it also shows that maybe the API wasn't really thought through completely. So over here, we have the map setter service and path generator service. And those are two servers that execute the setMap service and generates path service as callbacks. I know it's a mouthful, but that's the naming convention I went with. So let's take a closer look at one of the functions which actually is used as a callback function for the service. So over here, we can see that response is an out parameter that is set in the function. And if you just look at the call signature of this function, it's sort of impossible to reason about which one is an out parameter, right? And the reason I'm focusing on this is that CPP core guideline F20 states that a return value is self-documenting, whereas a reference could be either in out or out only and is liable to be misused. But I'm not saying that out parameters are bad by any means, but they have their place. Like optimization. And one person who knows a lot about this is my colleague Davide Facanti. So another thing that this function does is that error handling is done both by printing to logs and returning an error code via the service response. Keep this in mind because I'm going to talk about printing more later. We have this general global path function, right? And it's the function that generates the path and cannot be tested directly since it's a private method. But also it's a bit strange because you see start and goal arguments, but we also need to give it an occupancy map, right? But the occupancy map is a part of the class. So because it's a private member variable, this algorithm is tied to this class. So it can't really be used outside of this. So here's some limitations of the conventional approach as I see it. Just tight coupling between the path generated algorithm, well, in this case, the path generating algorithm and the runtime API. So in other words, because we inherit from RCL CPP node, the path generator is tightly coupled with the ROS2 API. And testing this code is challenging without involving ROS2 specifics, and you'll see that soon. And the path generator class is doing a bunch of things, right? It's managing ROS2 communication, it's performing calculations, and it's implementing logic. This doesn't really follow the separation of concerns, and from your viewpoint, it can even be considered to violate the single responsibility principle. And also, this class seems to be inflexible to extensions. So implementing more features or handling more types of services will cause the class to grow quickly. And because the data are private variables, the algorithms are directly tied to this class. So, I mean, one example I can give is that what if we wanted to generate a path using a different path planning algorithm, right? We would need to spin up another server with a very similar logic. I guess a different option for extending this class, though, is to inherit from this path generator class. But the thing is, that will increase the inheritance change, and it sort of makes it harder to reason about. So now let's get to testing the conventional approach, as I said it, right? So testing the conventional approach requires creating runtime clients to send requests to the path generator class, or path generator service, right? And this is something you don't really want to do in like your tests invoking middleware. There's additional utility functions that are needed to keep the test concise, but also this additional code invokes the runtime environment. I do want to note one thing. So note that for this test fixture class, that our CLCpp node is a member variable. This is another common pattern that you see in ROS2 code to create an interface with the ROS2 API. But it still sort of ties the class to the ROS2 API. So with that, let's take a closer look at the sendPathRequest function, which is a utility function used in the tests. So over here, first we have a loop that waits for the service to become available. SendPathRequest sends an asynchronous request to the generate global path service. And you can see that involving middleware into the testing process is where flakiness can be introduced. So the reason why flakiness can happen is that because once we invoke these functions that these middleware functions, that sends out a network call, and once that is gone to the system, that's outside of the code's control. And if the network doesn't, if the network doesn't decide to process that call right then, that's, things can time out and things of that nature. So that's where flakiness is primarily introduced in ROS2 tests, right? Excuse me. So what we want to do is that when unit testing core logic, we want to avoid this inter-process communication. So now that I've laid all of this out, let's look at a test. Sorry if the code is too small. So this test, it verifies that the path generator will return an empty path if it cannot find a path between a start and a goal position. That's why the name of the test is no path, self-documenting code and everything. It requires creating a thread that executes the callbacks for the path generator server. It sends 2 requests, one for setting the map and one for generating the path. And each request blocks until a response is received or the request times out. Finally, through all of that, we can test a response from the path generator service. But wait, it's not finally yet, because if we don't deal with the executor and thread, then we can get a use after free error, which can lead to a seg fault. So look just in the simple test. We want to test if our path generator server doesn't generate a path, and we have to have all this set up. We have 4 places where flakiness could be introduced. Is there a way to refactor the code so it can be tested without invoking the middleware? I mean, I guess if there wasn't, I wouldn't be up here giving a talk, right? So let's get to that. So now I'm going to talk about functional programming principles. So what is functional programming? It's a programming paradigm characterized by the use of mathematical functions and avoidance of side effects. And a side effect is anything a function does that is not observable through its return value. Functional programming is identified by the use of higher order functions, pure functions, monads, and declarative syntax, among others, right? But the thing is, C++ has all of these, it has the tools to implement all of these already, including lambda functions, stud function, stud optional, stud expected, and more. So what we want to do is we want to maximize the use of these features to write code with a minimal number of side effects. Note that I said minimal. Ideally, we would want 0 side effects, but that would just turn our computer into a space heater because it's not really interacting with anything. So let's go over some of these principles and how we can apply them using C++. So the first thing I'm going to talk about is pure functions. A pure function is a function that is, one, deterministic. For the same it always returns the same output for the same set of inputs, right? And two, it has no side effects. So they don't alter the state of the program, global variables, or produce any observable interaction with the outside world, such as writing to files or displaying output. Why is this desirable? Well, one, it's really easy to locally reason, right? The code can be understood just by looking at the portion where the pure function is called and the limited scope around it, because the pure function doesn't, well, I'll get to it. And two, testability. Testing a pure function is trivial. You make the required inputs, you run it through the pure function, and then you check the return value. Practically, pure functions do not contain state, right? So they can't have static variables, and they don't really interact with the class member variables inside of the function. And two, they don't mutate input parameters. So here's a funny way of thinking about a pure function. A function is pure if and only if it could be replaced by a lookup table, potentially infinite large, because if you know the inputs, then through a pure function, you're going to know what the output is, right? So over here, I'm going to look at some impure functions. And what I got is a simple implementation of a smoothing filter. So like I said, none of these functions are pure. And sometimes the reason about why a function isn't pure can be sort of subtle. So over here, we have get timestamp. And it gets the time from the local machine. That is an input side effect because we're reaching out to the local machine to get the time. Each invocation of get timestamp will also almost always return a different value, right? Because we have no inputs and we just call it get timestamp. We get the timestamp back as a string, and if you call it again right after, it's going to give you a different timestamp. We have a log over here, and that prints directly to the console. That's considered an output side effect. Over here, we have a filter function, and it contains state with a variable that is initialized in the lambda capture. So with that, what happens is that if we run filter multiple times with the same input, it returns different outputs. First time, you can see that it returns 0.7, and second time, you can see it returns 1.0. The thing is, though, I just want to note that this is the desired behavior of the function. It would have been better for this function if we actually provided the x previous value as a argument instead of keeping it as state inside of this value, inside of the filter function. And finally, filter time series has an out parameter that's modified. One of the things I said for pure functions is that we can't mutate input parameters, right? So that's everything about pure functions. Now we're going to talk about closures and partial applications. A closure is a function object that has an environment of its own, and it keeps track of the variables captured from the outer scope. A closure can access and manipulate these captured variables throughout its lifetime. And some of you might be thinking that this sounds really familiar. Yeah, it's essentially a lambda capture. So partial applications are maybe, I guess, a bit more complicated, but it's a concept in functional programming where a function is fixed with a certain number of arguments, producing a new function with a lesser number of arguments. So I'm going to talk about this code now. Here you have some code that shows both lambdas and partial applications. First, we have this lambda function that multiplies two numbers. So that's the multiply lambda function. Then multiply by two captures that multiply function. Then multiply is partially applied in multiply by two by fixing the first argument to 2. Now we can just call multiply by 2 by giving it one input argument. And that's a sort of an example of partial applications. But I can do a bit better, right? So here's more code that shows closures and partial applications. So isOccupied is a lambda function in plan that checks if a cell in a map is occupied. IsOccupied captures the input parameters and all variables that come before it by reference. That's a closure. Planner is a Lambda function that captures map and partially applies that map to plan. So now that we call this a planner function, all we need to do is give it the start position and the goal position. And because we've partially applied the map, it doesn't need that anymore, right? That reduces the number of required input arguments. So next, I'm going to talk about higher order functions. A higher order function is a function that can, one, accept other functions as arguments, or return functions as a result. So just a little bit of clarification, a higher order function can do either, or it can do both of those things. Why is this desirable? So one thing is higher order functions have a lot of modularity and reusability. The behavior of the function is configurable, and they can be used in different contexts. And another thing we can do with higher order functions is control flow abstraction. So control flows like looping and conditional execution can be abstracted in a readable and reusable manner. And one thing that I'm going to tie back to is testability. Smaller, well-defined functions are easier to test. So one thing to note is that the STL, or the standard template library, has many higher order functions. If you guys went to Klaus Eagleberger's talk earlier today about algorithms, he did a great job explaining them. So, there's higher order functions in the STL such as stud transform, stud find if, stud copy, and more. So let's look at some higher order functions in the STL. So over here, I have like this toy example. So what this code does, it multiplies each element of a vector by 3 using stud transform. It removes any element less than 5 using stud remove if. One thing I want to note is that remove if actually moves the elements that were not removed to the beginning of the collection and returns a past the end iterator to the new end of the collection. That's why in the next line you see that the input is resized. And using stud accumulate, it sums up all of those elements. So the 3 algorithms that I use, transform, reduce, if, and accumulate, are very common in the functional paradigm. So just for, I guess, a bit more of an explanation, transform applies a function to each element in a collection. Reduce if removes elements from the collection, and accumulate sort of converts that collection into a scalar. So canonically in functional programming, they're known as map, filter, and reduce. And one thing I hope you notice and appreciate is that using the declarative syntax of these algorithms in the STL, it makes the code really easy to understand. We know that for stud transform, we're trying to triple the numbers just because we're passing in a lambda that's called triple, and it's easy enough to understand that remove if is removing certain elements and things like that, right? So pretty easy to understand. So with that, higher order functions are extremely flexible. So here's a simplified implementation of a trajectory generator. So we can see that generate trajectory is a higher order function. How you ask? It's because it takes in a function of type waypoint generator. In main, interpolate is actually passed into the generate trajectory function. And this type of trajectory that can be generated is customizable by passing in a different waypoint generator function, showing how flexible this generate trajectory function actually is, right? Next thing I want to talk about is monadic error handling. So monadic error handling is a functional programming technique for dealing with errors in a clean, compositional, and type-safe way. So what this does is the approach encapsulates error handling into types and operations on those types. So the question you might be asking is, why is this desirable? So one thing is it has type encapsulation. Monadic error handling encapsulates the result of computations along with the possible errors within a single type. It's a compositional error handling. So monadic error handling allows composition of operations that might fail in a way that if any operation fails, the whole computation fails. So I swear I'm going to explain this later, but we'll get to it. Another cool thing is there's error propagation. Errors can be automatically propagated through a sequence of computations until they are explicitly handled. So let's look at some ways to handle errors before we explicitly look at monadic error handling, right? So here is some code that shows some ways to handle errors. So what's the first way to handle error? By doing nothing, right? You just let the error happen and the program terminates. The method that most people are probably familiar are with throwing exceptions. In this case, we try to divide by 0, and the function throws a domain error. To make sure that the program doesn't terminate, though, we have to wrap this code, or the code that might throw in an exception, or the code that might throw an exception into a try-catch block. The thing is, though, a try-catch block sort of takes us out of our normal control flow, and it's not really desirable. I'm sure everybody knows, but error codes are also a concept where the function returns an error code and sets a results via an out parameter. But with error codes, they can be a part of your control flow, as they don't really step out of the control flow as an exception would. But there's more ways to handle errors these days, right? We can use stud tuple and stud optional. So with stud tuple, both an error code and results can be returned. In practice, though, people tend to ignore the error code. And I guess for a bit more technical information, stud tuple is a product type. And it might not really be desirable to return stud tuple because the types contained by the tuple must be constructible, which might not be trivial, and if you have an error condition, you might not be able to construct them, right? So another cool thing is stud optional. And with that, we return something that either contains a value or is empty. So is there a way to either return a value or an error code and tailor our future operations depending on the return? Well, yeah, I guess I wouldn't be talking about it if there wasn't. So here we have monadic error handling. So monadic error handling is the functional programming concept of returning a type that can either contain an expected value or an unexpected value, and then composing operations depending on that value. Yeah, it might be tough to parse, but I'm going to go over some code and that shows an implementation of monadic error handling, right? So over here we have divide, and it returns a monadic type, which either contains an int or an error code. If the divide return contains an int and then takes the expected value and passes it to print value. If the divide return contains an error code, or else takes the unexpected value and passes it to print error. So this is actually a great method of removing logs from library code, because if your library function returns a monadic type, then the return can be directly inspected for errors, right? So this method of chaining operations is sort of fundamental to functional programming. And another thing is look how much nicer things look, right? With the declarative syntax. And it's easy to know in the line where we're dividing what's going to happen. We either print value if it's successful or print an error if it isn't successful. So how does functional programming help, right? It lends itself to the minimization of mutable state, which is something we should, I think, always strive for. Testing is easier with pure functions because only the return value of the function needs to be evaluated. It's rather trivial, I'd say. And different functions can be passed as arguments to higher order functions, lending itself to modularity. And another thing, monadic error handling simplifies error checking. So given all this, let's try and refactor path generator. And I'm going to make a claim. And I'm going to say that the refactored path generator has 100% coverage, meaning that every branch in the refactored path generator can be tested. So let's get to refactoring. So just as a refresher, this is how our current path generator looks. We can see that, so in our code, right, an RCL CPP node type object can be constructed in main and services can be assigned at that point. So there is no need to actually have a path generator object that inherits from RCL CPP node. So in the class, we have this create service method and accepts and that accepts class methods, free functions, and Lambda functions. And the thing is, excuse me, the private functions of a path generator can be turned into free functions and Lambda functions. So I hope you can see where I'm going to go with this, right? So let's try to refactor the callback function for generate path service. So this is how generate path service looks currently. So we can see that generate path service is one, printing errors. And like I've said before, that printing is generally a side effect operation. It's generating a path. And you can see that general global path accesses the occupancy map through this class. So it has hidden parameters and is tied to the class. And it's also setting an out parameter. If we're trying to follow functional programming, we're trying to minimize mutable state. So let's try to see if we can get rid of the out parameter, right? So with this is going to be our refactoring strategy. Let's try to isolate the error printing functionality to another function, right? If you want to do that, that means that the error printing function needs to have like an error code or something passed in. So the object held by the shared pointer can be assigned by another function. And that, in this case, changes mutable state into a return from a function. And the generate global path function and all of the associated prechecks, let's extract that into another function. So our goal for this refactoring is to refactor the code into its core functionality, which can be expressed via pure functions, and side effect bearing code. So here we have the refactored core functionality. So first, we can see this function returns a type which can be used for monadic error handling. If there's an error, the function can handle the error in a compile time checkable way. And with this, we can also see that the side effect of printing has been sort of abstracted into a higher layer. Side effects should generally be sort of pushed to the edges of your code so they can be seen in the topmost layer, because nobody wants to be like 10 function deep into like a stack trace to figure out why like a variable is being changed, right? And also with the monadic error handling, we can sort of decide where the error goes. The function that generates the path can now be passed in, making this function a higher order function. So the path generator function now takes the occupancy map as an argument so that the hidden parameter is now gone, it's exposed. In the field of robotics, it's sort of common to change path planners at runtime depending on the situation. So that's sort of this sort of like architecting code this way sort of lends itself to that. I also want to note that passing the function like this is an example of the strategy pattern, and that is generally used when we want to have like really extensible code, right? So another thing is this function is deterministic and has no side effects, so it's a pure function. So let's go ahead testing it. So testing the function is now fairly trivial, right? We create our required parameters, we pass the parameters into the function under test, and we check the return. All the functions that have been refactored so far can be tested this way. And now everything can be put together for the callback being executed by the generate path service. And the important thing to note is all this has been done without invoking the ROS2 API in our refactored code. So the generate path callback function, we're going to replace it with a Lambda function. If a generate path returns the expected value, it is directly assigned to response. If generate path returns an error, though, the error is handled by chaining functions together. And that's due to returning a monadic type and performing monadic error handling. So if needed in like our function, function call stack for monadic error handling, we can sort of extend that. We can add more functions to manipulate the expected type or error type, which increases our modularity. And also pretty interesting to note is that with declarative syntax, it's easy to sort of know what the function does without like sort of introspecting the code, right? So we can see that print error probably prints an error. A return empty response returns an empty response, and stringify error takes our error code and turns it to a string. So it's really nice to be able to just look at code and know what it's doing without getting into all of its guts. But the thing is, though, we have this Lambda function. How are we going to test it? with dependency injection. So dependency injection, or DI, is used to move or inject objects into another object, right? So the thing is, though, we're trying to minimize mutable state, but we still need mutable state. So to keep track of the occupancy map, thus map is a member variable. For the manager object, we have this middleware handle struct, and that's going to be the interface for our injected dependency. This abstract interface can also be used to implement each function using the ROS API. And the Lambda function that I was showing previously can be used, or the Lambda function that I was showing previously that is being used for the generated path service can be captured via mocking and then tested. So here's the code. Here's the code that we're going to test. Sorry. We have this test fixture, and it calls the callback function for the sets occupancy map service when a mock function is executed, right? This test fixture also captures the callback function for the generate path service, so it could be executed later. So, sorry. For this test, the occupancy map has already been set via the test fixture. So using the test fixture, the cost map is set when the mock middleware handle is moved into the manager object. And the generate path callback can now be tested by executing the callback function directly. So here's the big takeaway. There is no invocation of middleware using DI, and all code is testable without invoking the ROS2 API. So here we get to our conclusion. So the thing is, the refactored tests are deterministic. They cannot be flaky because they do not invoke the middleware at any point, right? What we want to do is we want to break down code into discrete components that can be tested. We want to sort of prioritize using pure functions because they're easier to test and reason about. And using higher order functions increases the modularity of our code, in this case allowing for different path generating algorithms to be used. And with Monadic error handling, it's sort of led to easier error checking, right? We can just sort of compose the functions of how we want to deal with the error or the expected type. So refactoring path generator using DI in conjunction with the functional programming paradigm led to code that has 100% coverage. I want to give thanks to all these people and Picnic. And with that, I'm opening the floor to questions.
What C++ version are you using?
This was, so StudExpected, I think, actually is CppCon23, but if you don't want to use that, all the code was written using C++20, I believe.
20?
Yeah.
Okay. Just same part as a comment, I don't come from robotics. I was looking for a really good presentation on functional programming. It's the first one I've seen that used expected. And this was really, really good example. Thank you.
Yeah. Oh.
Hi, thanks. Yeah, this looks very familiar to me from what I work on, and I really want to get to like where you showed you can get to. I'm just wondering, did you encounter any like organizational pushback from like object-oriented, like this is how the documentation shows we should do it, we just want to do it this way?
Not particularly. I think with Picnic, especially, we tend to work on small teams, so we sort of have like the freedom to architect our code as the way we want it, as long as our like client agrees, right? So that's really nice.
Do you live in both worlds for now? Are you like all the way here? Or?
I mean, I tried to tend toward this style, but if the client is like, no, our code base is this way, then it is what it is.
Okay, great, thank you.
Yep.
Hi, Bilal. Thanks for the talk. Could you give the name of the library that you're using to polyfill StudExpected so you can use it in C++17?
Yeah, so for this code, I sort of Control F and replaced StudExpected by TLExpected, and that is that has Monadic, types and Monadic error handling, and it's available in C++17. So for reference, if you want to use this with C++17, just Google TLExpected. Really nice.
Hey, great talk. Just a quick question. Have you guys, either you individually or the rest of you guys at Picnic, made any pushes towards the broader ROS2 ecosystem to kind of replace the original examples with these more functional approaches?
Well, I'm going to be giving this talk at ROSCon, so we'll see.
Good luck.
Thank you. I have some time left, so if anyone has questions.
Yeah, no, this is interesting. It's also very applicable to like kind of what I'm working on right now. We're driving for a much more functional approach to our nodes, especially like certain nodes within the robotic system that like don't actually need any state. And so the one thing I've run up against that is interesting is like the only state that ends up remaining in like a fully, functionalized node is like some upfront config parameters that maybe are like read from a file or read from a config file at the beginning, and then persist for the life cycle of the robot running.
Yeah.
Do you have any thoughts on like how to like maintain that stateless that statelessness while being able to properly encapsulate and not just like make globals to store your config parameters?
That's a good question. I think, there are times where you sort of can't get away from state. Like, in my example, I had the manager function hold the map variable. So I think one of the things I would look for is that, so side effects code, we're trying to push it like to the highest level of abstraction, right? So if that's where like all of your state is gonna live, I think it's better there than like deep inside of like your call stack, right?
Yeah, correct. But this would be something like doesn't change for like the life cycle of the program, right? So it'd just be read up front, but it gets used, but not.
Yeah, I don't know. I'd have to think about them more. So
Okay.
sorry.
Just curious.
Yeah.
Thanks.
Alrighty, if no one has more questions, that's it.